Hi everyone, this is the SI video um, for the fifth SI session. So in this SI session, we were we went over a lot of the deals out of the reaction from lecture, and then we also spoke about aromaticity. So just some basic concepts um, were covered, and so this first question asks us: circle the diene, and it can be more than one that's a diene. So you can go through your notes right now, um, see what a diene is. Maybe you can answer this before me. Um, but what I usually use to identify a diene is double bond, single bond, double bond. So if we look at A right there, we can see that it's double bond, single bond, double bond, right? So in that case, A is a diene. So B is not a diene. It's just one double bond. Um, B is actually a dienophile, right? So what about C? It has that NO2 group, and we might get a little bit thrown off by it, but in the end, it still has a double bond, single bond, double bond. So it's also a diene. And what about D, right? Is it a diene? Because there's this double bond right here with the carbonyl. It actually is not a diene, right? Now, number two, circle the dienophile. So dienophile is going to be the one that is just basically a double bond. That's really all we're looking for. So A is actually a diene. It's not a dienophile. B is a dienophile, has a double bond right there. And then C is a dienophile, has a double bond right here, right? And then what about D? So as we learned in lecture on Tuesday of this week, if you're going through your notes, Tuesday would be 2/11, February 11th. We learned that triple bonds, alkynes, can also do Diels-Alder reactions. So this would also be a dienophile, right? So what is the mechanism of the Diels-Alder reaction? It's in 3 steps, and it's pretty simple. The first step is that this bond goes over here. Oops, that was a little bit ugly, but you get the idea, right? That bond goes over there. This double bond from the dienophile goes over here, and this double bond from the diene goes right here, right? So what we're going to form is we're always going to form one ring. But when we have something like this dienophile, when it's already in the ring, we're going to form 2 rings, right? And you have the double bond that was retained right there, right? And you're going to have the substituent, which was just a carbonyl, right? Okay, so now question number 4 is going to be the exact same thing. So this double bond goes right there. Now right here, you have an alkyne as a dienophile, but it's the same mechanism. And then this double bond goes right here. But right here, you're going to note when I start drawing this, that not only are you going to retain the double bond from the diene, you're also going to retain a double bond from the dienophile. It's going to look like that, right? And then you have the substituent to draw. Looks like that. And then the substituent for the diene is just something like that. And then the NO2 group. right? Okay. Let me draw a little bit closer, just to not confuse you guys. NO2 group. So now we're going to do number 5, draw the product, and we're going to ignore, oh dang, we're going to ignore endo and exo forms, right? So again, you can draw out the mechanism. I'm just going to draw out the product. Actually, no, for this first one, I'm going to actually draw out the mechanism with you. So we want to focus on the carbons here. Let's see, this is carbon number 1, number 2, number 3, 4, and 5, right? So, and excuse me, I'm getting a little bit sick. So this double bond between carbon number 1 and 5 is going to go right here, right? Between carbon 1 and 2. And then you have the double bond between 2 and 3 is going to go here. And the double bond from the dienophile is going to go right here. Okay? So essentially what you have here is the following product. So carbon number 4 wasn't even touched, right? So oops, I'm trying to zoom out. So carbon number 4 was not even touched, right? So we can draw this exactly like we had it. And that's usually what I do. That's easiest for me. Exactly how it was before. Except now that reaction is done. So again, carbon number 1, carbon number 2, carbon number 3, carbon number 4 is untouched, and carbon number 5. What's actually going to be new here is that we're going to add on the dienophile. But the dienophile is only going to be added to carbon number 3 and carbon number 5, right? And so what's the easiest way to draw the dienophile? I honestly just draw it like a square. And so we know the dienophile is only attached to the diene at carbon number 3 and number 5. So you can just draw a line like this from carbon number 5 and a line like this from carbon number 3, right? So if this makes it easier, I'm going to number this out. So let's say this is carbon number 6 right there, carbon number 7 right there. So this is carbon number 6 right here, carbon number 7 like that. So take a minute to look at that. So at carbon number 6 right here, we have one NO2 group. At carbon number 7 right here, we have another NO2 group, right? So I'm going to erase those right there. And now we know that we have 2 NO2 groups coming off from here, right? And there it is. That's it. And if you want to number it again, we can do that. This is carbon number 6, carbon number 7. So that example was a little bit more thorough, just so you guys can see how the mechanism goes when the diene is cyclic. Excuse me. So I'm going to do that one more time just so we can recognize how to draw this. Okay, so carbon number 1, carbon number 2, carbon number 3, 4, 5, and 6. And we can do this as carbon number 7, carbon number 8. So again, we have 6 carbons in the diene just because that's a hexane or a hexadecimal diene, right? Because it has 6 carbons. So that's why we got 8 carbons in total instead of 7 in the last molecule, or in the last reaction, just in case you were confused. So again, what's going to happen is that carbon between 1 and 6 is going to go right here. I'm sorry, the bond between 1 and 6 is going to go right there. The bond between 2 and 3 is going to go right here. And the bond between 7 and 8 is going to go right here. So carbons 4 and 5 are completely untouched, right? So you could honestly just draw the molecule completely untouched with the double bond between 1 and 2 to start off. So that's usually what I like to do. So here we have that molecule, right? And we have carbon number 1, 2, 3, 4, 5, and carbon number 6. Now, carbon number 5 and 4 were not even touched, but carbon 6 and carbon 3 were attached to the dienophile. So carbon 6 was attached to the carbon number 8, and carbon 3 was attached to carbon number 7, right? So having that in mind, we can draw the rest of the molecule like so. Oh dang, wrong carbon, right? Just like a little square. And you know that this is carbon number 7, this is carbon number 8, right? And then you just have your CF3 group and your other CF3 group. That's ugly, but you get the idea, right? Actually, it's going to be in the way in the next molecule. So let me do that again. CF3 and then CF3, right? Okay. So now for these other molecules, I'm just going to go ahead and draw the product, since I hope we're pretty clear on the mechanism at this point. Make this a little bit smaller, just so I can work. Alright, so we have this, and then we have our 2 NO2 groups attached to each of the carbons from the dienophile, right? And then this oxygen is untouched. Right, so now we can do reactions 8 and 9. And so for 8 and 9, we're just trying to see what the difference is between these reactions, because they're fundamentally the same reaction, right? You have your benzene ring, and then you have your hydrogen with your nickel catalyst. But for number 8, you only have a very high temperature, and you don't actually have a very high pressure. So for number 8, you would get this molecule, right? Nothing happens. But for number 9, since you have high pressure, 25 atm, and high temperature, then you're going to get this reduction in double bonds, right? So it goes from a benzene ring to a hexane, okay? So for number 10, we're going to draw the molecular orbitals from these atomic orbitals. So it says it's two products, right? So what two products could I be talking about? So whenever you have two molecular orbitals, you can do the math. It's going to be something like this. Two atomic orbitals are going to give you one anti-bonding molecular orbital plus one bonding molecular orbital, right? So two atomic orbitals are going to give you one anti-bonding molecular orbital and one bonding molecular orbital. So the bonding molecular orbital is pretty easy to draw, just like that, right? And the anti-bonding molecular orbital, draw like that. And then you can draw a little node, and the other one like that, right? So just to reiterate, two atomic orbitals is going to give you two different molecular orbitals, one bonding and one anti-bonding, right? Okay, so So problems number 11 through 17 is just determining between aromatic, anti-aromatic, or non-aromatic. Sorry, I put counter. Non-aromatic, right? So the first thing I want you guys to do is to look through your notes, see the rules for aromaticity. Since I already, let's do this. Since I already used all of this, I'm just going to kind of put that right there. And we're going to write out our rules for aromaticity. So our rules, right? So in order for a molecule to be aromatic, it has to be planar. And planar just means, sp2 hybridization on the carbons. Number 2 is that it must be conjugated. So conjugated. And rule number 3 is going to have to follow Huckel's rule. Huckel's rule is 4n plus 2. So in class, we kind of went over what Huckel's rule is. And a question arose that said, what does n stand for? Well, like Dr. Plummer said, n stands for actually any integer that you may think of. It can stand for 2, or it can stand for 2,000. It doesn't really matter. It's just an integer, and it comes from basically nowhere. But the Huckel's rule, 4n plus 2, is going to help us in deciphering what the adequate number of electrons is for a molecule to be aromatic. So basically, let's just retain that 4n plus 2 rule, right? So put this over there somewhere. So 4n plus 2, right? And let's do this. Let's do 1. So let's do n equals 1, right? And that is going to give you 4n times 1, or 4 times 1 plus 2, which equals 6. If you plug that 1 into this equation up here, right? So if we do n equals 2, and again, these are just integers. They don't come from anywhere. N does not mean, let's do this. N does not mean the electron number, and n does not equal the double bond number, n is just an integer. So if n equals 2, then the 4n plus 2 rule means that the equation is going to equate to 10, right? If n equals 3, then we're going to get 14, right? And so the easiest way for me to understand Huckel's rule is to understand that these numbers right here just correspond to the number of electrons in an aromatic molecule. So for example, we all know that benzene is aromatic. And how do we know that? Well, we know because we've been told that it's planar, so all the carbons are sp2, and we know that it's conjugated because, for example, if this bond goes right here, then this bond goes right here, then this bond goes right there, right? So we know that it's conjugated and we know that it's planar, but how do we know if it's aromatic? Well, does it fit in with Huckel's rule? 4n plus 2. So Huckel's rule is this one, right? So how many electron pairs are there? There's 3 electron pairs. Right? And how many electrons total are there? There's 6 electrons participating in those 3 electron pairs. So what I take this to mean is that this molecule is indeed aromatic because it does satisfy Huckel's rule. Because if you see right here, this 6 and this 6, right? Another way to think about it is a rule that we learned in class, that a molecule is only aromatic if it has an odd number of electron pairs, right? An odd number of electron pairs. So benzene has 3 electron pairs, so it's aromatic. All right. Hopefully, as we work through these problems, I'll be able to better explain. Okay. So, number 11. So let's assume it's planar and sp2 hybridization on each carbon. Is the molecule actually conjugated? So you can take this time to work it out by yourself. But indeed, it is conjugated, So what I always do to see if it's conjugated, it might not be the best thing to do, but I do it anyway, is I just start shifting these double bonds, right? And I start shifting them everywhere. And if it works out like that each double bond can be moved to the side one time as one comes after it, then I say that it is conjugated. Okay? So now we know it's planar, sp2 hybridized, conjugated. Now we can use the last rule that we thought about. How many electron pairs does it have, right? And is it an odd number of electron pairs? And if so, then that rule is satisfied. So we have 1, 2, 3, 4, 5 electron pairs. So it's an odd number and it is aromatic. Moreover, another way to think about it is through Huckel's rule. So 4n plus 2. So we had done the filling in of the equation to get us the following numbers: 6, 10, 14, right? And I take these numbers right here to signify the number of electrons. Not electron pairs, just electrons. So if this molecule right here has 5 electron pairs, then it's going to have 10 single electrons because each electron pair has 1 electron. So by this molecule having 10 electrons, it satisfies Huckel's rule. Okay, so let's actually think about this in a different way. I probably should have done this a little bit earlier. So, actually, let's go back to that problem real quick. So this molecule is in fact aromatic, right? Because it's conjugated to sp2, it satisfies Huckel's rule, and it has an odd number of electron pairs. Okay, so let's think about Huckel's rule again. 4n plus 2. But now let's say that we have the following molecule, right? So we have 1, 2, 3, 4, 5, 6, 7, 8 carbons, and we have 4 electron pairs, and we have a total of 8 electrons. So is this molecule aromatic? If we go through one of our rules, which says that we need an odd number of electron pairs, then we understand that this molecule is not aromatic because this molecule does not have an odd number of electron pairs. It has an even number of electron pairs. So it's not aromatic based on that category, period, right? But we can also think about this through Huckel's rule instead. So is there any integer any whole integer that you can get when you plug in that 8 into Huckel's rule? So if you have this equation, will n be a whole integer? And if n does not equal a whole integer, and a whole integer is just like 1, 2, 3, 4, right? And a whole integer is not like a fraction. So if n does not equal a whole integer, then that means that Huckel's rule is not satisfied. So in other words, we can just do the math, right? 4n is equal to 8 minus 2, which is 6. So it means n is equal to 6 over 4, n is equal to 3 over 2. 3 over 2 is not a whole integer. So that means that Huckel's rule is not satisfied because this number of electrons plugged into Huckel's rule does not give a whole integer number for n, right? So I hope I'm making myself clear. I really hope so, but let's try to work out through some other problems to see if we can better understand aromaticity, right? So at this point, hopefully you've also looked at criteria for a molecule that is anti-aromatic and for criteria of a molecule that's non-aromatic, right? So what about this molecule right here? Number 12. Is this aromatic or anti-aromatic? So you have basically in the whole molecule 3 double bonds. But double bond right here is not participating in what we can say the conjugation of the molecule, because it's just a double bond right here. So it's not participating, which means that this molecule is not conjugated. This is different if the molecule looks something like this, for example, right? Where you had the lone pair participating in the conjugation, which means that you could do this, put this molecule right there, put this molecule right here, put this double bond, this lone pair somewhere else, and now that molecule is conjugated. Anyway, so we know this molecule is not conjugated, so right off the bat, we know it is not aromatic. But is it anti-aromatic or is it non-aromatic? So basically the criteria for anti-aromatic, let me do this right here. Criteria for anti-aromatic is that the number of electron pairs is even. If the number of electron pairs is even, but the molecule is conjugated and the molecule is planar and it fulfills, just think about it this way. It's anti-aromatic if the number of electron pairs is even, and it is non-aromatic if the molecule is just not conjugated, or it's not planar, right? Whereas anti-aromatic molecules are conjugated and they are planar. So from here we can see that probably it's going to be harder to discern between an anti-aromatic molecule and an aromatic molecule than between an aromatic molecule and a non-aromatic molecule, just because non-aromatic molecules are pretty easy to give away, because they're not conjugated. So anti-aromatic molecules, they are conjugated, they are planar, they just have an even number of electron pairs, right? Non-aromatic molecules are not even conjugated and they're not even planar. Okay, so in regards to Huckel's rule, anti-aromatic molecules are not going to satisfy Huckel's rule, right? So we had talked about the what did he call it? The stopsynodiene that Dr. Plummer drew, right? Like this. And we had drawn it with 4 electron pairs. So this molecule is actually conjugated. This molecule is planar. But this molecule has an even number of electron pairs. 1, 2, 3, 4. 4 is an even number, which means this molecule is anti-aromatic, right? So let's draw this molecule again. What if this molecule was actually drawn like this, for example? Even though it has an odd number of electron pairs, this molecule is not even conjugated, right? Which means that this molecule is non-aromatic, right? So I hope that kind of helps you guys understand the difference. But now let's go back to the problems. So we saw from number 12 that this molecule is not even conjugated, right? So non-aromatic. What about 13? Is this molecule conjugated? Think about it for a second. So this molecule is actually conjugated. If you move this bond right here, and you move this bond right here, then your double bond moves right there, right? So your molecule is conjugated, and your molecule is planar. But your molecule has an even number of electron pairs, which means that it's anti-aromatic. Okay? So what about number 14? So for number 14, let me state that a molecule like this one, where it has two sets of electron pairs, like that. So the electron pairs on the inside, right here, participate in the conjugation of the molecule. And conversely, the electron pairs on the outside do not participate in the conjugation of the molecule. So with that in mind, we see that we have this electron pair participating, and we have those other two electron pairs participating. The molecule is actually conjugated, and it is planar, and it has an odd number of electron pairs. So it has 3 electron pairs. That's good. But then, does it satisfy Huckel's rule? So 3 electron pairs means it's 6 electrons. And like we stated before, Huckel's rule, 4n plus 2, if you plug in 6 here, then you have 4n equals 4 when you subtract 2 from 6, and you get that n is a positive integer. So that's good. It does fulfill Huckel's rule. So molecule in number 14 is actually aromatic. All right, what about number 15? So I forgot to draw here. Let's do this. I actually forgot to draw the 2 electrons on the outside right there. So this molecule is planar. If you move around the bonds, it actually is conjugated, right? Now, it has an odd number of electron pairs, so that's good. But does it follow Huckel's rule? So if we have 5 electron pairs, which means we have 10 electrons in total. So again, if we do 4n plus 2 equals 10, does this give us a positive integer? So we have 4n equals 8, so we have the n equals 2. So we have a positive integer, we have an odd number of electron pairs. This molecule is aromatic. So now let's work on the last molecule. Right off the bat, without even knowing if it's conjugated or planar, or if it fulfills Huckel's rule, we see that it has an even number of electron pairs, which means that it's actually either going to be anti-aromatic or non-aromatic. So remember, for a molecule to be anti-aromatic, it has to be conjugated, planar, and have an even number of electron pairs. For a molecule to be non-aromatic, it just does not fulfill these first two. So for a molecule that's non-aromatic, it's not even conjugated and it's not planar. Not conjugated, not planar. Right? So you can look back at those definitions. But this molecule is actually conjugated. Oops. And you can shift the bonds around, and it is planar. It just has an even number of electron pairs. So this molecule is anti-aromatic, right? And you can look back and compare and see if you can do this by yourself and justify why these molecules are each their designation.